In this screencast, I want to do a quick review of Dijkstra's algorithm and then go on and give a fairly formal proof of correctness. If you're not interested in the review, then just skip ahead to slide 5. Here's a quick overview of from a high level of Dijkstra's algorithm. Again, the idea is you are forming growing trees, one vertex and edge at a time, and the way you grow the tree is you add the vertex and its associated edge that gives you the shortest path to that vertex. So you're uncovering the vertices basically in order of the length of their shortest paths. The way you're going to do this, I'll go into in more detail on another slide, but basically you just have a loop in which you have a known shortest path tree, set of vertices that you know the shortest path to, and then each time again you find the shortest path from the start to a vertex that's not in VT and you add that edge to VT. Generally speaking, when you implement this, what are you going to have to keep track of? You're going to have to keep track of the vertex that you're adding and basically the previous vertex that you know the shortest path to already. This is tantamount, basically the same thing as knowing the edge, right? Because you got the vertex and then you got the other vertex that's on the edge. And so typically to initialize this, we'll just set the distance of all the vertices to be infinity and previous into null. So this infinity, or very large number in a computer, just represents the fact that we don't have any, we don't know its shortest path, and moreover, we don't even have a path to it yet. So as we're going, we're finding paths to vertices, and at each step of the way, we're going to be doing what's called relaxation. We're going to find new paths. If we don't have the shortest path already, we'll find new paths that potentially may be shorter than the current path, and if they are shorter, then we're going to update until eventually we end up with the shortest path. And that's basically, this is the modification of the previous slide that basically talks about that. And the way you do this is you traverse the adjacency list of the vertex that you just added and use that to update the tentative distances to the target vertex of the edges on the adjacency list of V. We'll look at the code here in a second and show this in a little more detail, and I'll go over it more carefully. Okay, now this slide shows the code for Prim's algorithm and Dijkstra's algorithm side by side. I'm just going to focus on Dijkstra's algorithm here, but notice if you go through this line by line, all the difference, basically, the only really real difference here is in the code down here. I'm sorry, the code down here in lines 9 and 10, where you're talking about the distance and potentially finding a shorter distance. In Prim, it's the distance to the current partial minimum spanning tree. In Dijkstra, it's the distance back to the start vertex. Hence, you have these this addition here. So again, if you go look at this, the guts of the program are while your priority queue is not empty. In other words, the priority queue is going to contain the vertices that you don't know the shortest path to. You get the one that has the minimum distance to it, which basically means that you now know its shortest path. You add that vertex to the shortest path tree, and then for each edge in that vertices adjacency list, you look to see if you can get to if you can get to U, the target vertex, any edge, if you can get to U faster using this edge than you could with any of the previous paths that you've explored. So the path, what's the path to U going to look like? The path to U is going to look like the path to V, which is the first vertex in the edge, plus the weight of the edge. That's going to be the length of this new path. And you check to see if the length of this new path is less than the length of the one you may have already discovered. And if it is, then you just decrease the length of the path that's stored That's the priority. So you're going to decrease the priority of U in the priority queue. In other words, you've now found a shorter path to U by using this edge VU. And again, just to reiterate, this new distance is the shortest distance from the start vertex to V, and then plus the distance from U to V using the current edge that you're getting from the adjacency list at this point. So that's it. I'm going to show some pictures of this to help you get a little more intuition about what's going on in the next few slides. So this slide shows basically the setup for when you're going to grow the tree, the shortest path tree, by an additional vertex and edge. So there are going to be this set of explored nodes. Those are denoted by this gray area. And then the unexplored nodes are out here. So, and basically the idea is you repeatedly choose an unexplored node which minimizes the distance. That means you have the shortest distance, and then you're going to add it basically add it to S, which is going to be the shortest path tree. Now, so let's see where that is in this picture. So in this picture, the current state of the world is all these, the shortest paths to all these vertices. And let's suppose that you go and you look in the priority queue, and V is the shortest distance away from of any of the nodes out here. Okay, so that's what's stored. These are all, right at this point, these are all tentative paths to all these nodes out here. So what happens in the algorithm is you pick V, because V's the minimum, has the minimum distance of all those nodes back to S, and then Dijkstra adds V to the shortest, the vertices that you have the shortest path to. So the picture comes over and looks like this. So again, we've added this path, starting at S, going to U, and then taking the edge U to V. This has the shortest distance in our priority queue of all these vertices out here, so we're going to add it to the shortest path tree. So the big question now is that really the shortest path? So is it the shortest path to V? Well, let's suppose that it's not, that there's some shorter path. Well, if you stop and think about it, it's got to be the shortest path from S to V using these nodes, right? Because we've compared the distance for any of, we've already gotten rid of this one. We've compared it to this one because it's got to be lower in the priority queue, and same thing for this one, it's going to be lower in the priority queue. Now, so let's suppose it's not the shortest path. If it were not the shortest path, then there'd have to be some shorter path that perhaps went like this. Pretend the arrow goes that direction. But if you stop and think about it, that really can't happen. Why can't it happen? Because you picked this particular vertex and edge by making this be the shortest path from S to anything outside the shaded area. But look, this is a path from S to something outside the shortest area. So this path already is bigger than this path, and then it's got to add these two additional edges. Now what makes Dijkstra work, and what's essential to the proof, is you can't have negative edge weights, because if you had negative edge weights, then in fact this could turn out to be shorter. So basically that's the entire proof. Now the next couple of slides are going to show lots of words around that proof, but that's basically the idea is that because the way Dijkstra picks this path, namely this is the vertex outside of the known shortest paths that's closest to start using a single edge, because that's the way Dijkstra picks it, you can't get a shorter path because that path would have to go through a vertex that's outside of the shaded part. So here we go on a more formal proof. I'd suggest definitely, at least for me, it'd be easier to read it, but I'll talk through it a little bit and make a few extra comments. But I think what you really need to do is study it and while you're looking at the picture at the same time and see how it works. So here's the idea. We're going to do an induction, and we're going to prove the inductive case by showing that Dijkstra's algorithm adds the k plus first shortest path, and thus has now found k plus 1 shortest path. In other words, the inductive the inductive statement is that at each stage k, we're going to have the shortest paths, the k vertices that are closest to the start. Okay, so suppose Dijkstra's algorithm does not find the k plus first shortest path, then there must be a shorter path than the one found by Dijkstra to some vertex which is not in the set of vertices reached by the kth shortest path. So then we're going to show that that proposed shorter path cannot exist because of the way Dijkstra works. So now I'll be a little bit more formal about the proof. We're going to mark vertices with an asterisk once we know, for the vertices for which we know the shortest path. And basically the proof is going to be an induction on the number of vertices for which we know the shortest path. So the base case, of course, the easiest way to do this is have an empty path to the start vertex that has length 0. That's obviously the shortest path from the start vertex to the start vertex. So there's no problem there. Now, for the inductive case, what we're going to assume is that we know that for k vertices, we know the shortest path to them, and we know what its distance is. Okay, and so what we need to do is extend that to k plus 1 vertices. So Dijkstra, how does Dijkstra do that? Dijkstra does that by adding to the shortest path tree the w that is the smallest length path given by something in the shortest path tree that we already know, plus a single edge. If you think about how Dijkstra is working, it's got the known nodes, and as it adds new nodes, it updates tentative distances to the vertices for which you don't know the shortest path. And so at this stage of the game, it looks at all those tentative distances to the nodes for which it does not know the shortest path, and it takes the minimum. And that minimum is given for that particular vertex by some path to some vertex that's known plus a single edge. Okay, so Dijkstra has found the shortest path to V star, and then this edge gets it to W, and this must be the shortest path of all the nodes of all the paths from S to W star using the shortest paths that we know are correct plus a single edge. All right, so suppose there were some shorter path. In other words, suppose P, and we'll call it P2. Suppose Dijkstra did not, the thing that Dijkstra found and put in its tree is not the shortest path. Okay, well, any path, so there must be some shorter path, S to W. Any path from S to W must cross the frontier between the nodes whose shortest path are known and the nodes for which the shortest path is not known. That was the picture I showed you on the previous slide. Let the edge in P2 that crosses the boundary, we're going to label that YZ. Okay. Thus, there's a path from S to Y star followed by the edge from Y to Z. And then there's got to be some additional path from Z to W. But let's dissect this now. The last section from Z to W of P2 has got to be bigger than 0, bigger than or equal to 0, since all the edge weights are non-negative. And the path length of the P2 that goes from S to Z, right? Remember, this is the first vertex outside the known area, the area of known shortest paths to vertices. That distance, S to Y star, okay, that's the shortest path from S to Y star, plus this edge, that can't be better, right? Because this gets compared back to this thing that Dijkstra picked. And Dijkstra picked the shortest ones of things that look like this. So this has got to be bigger than that. Okay, that contradicts that the vertex chosen by Dijkstra so this sentence here, this contradicts that the vertex chosen by Dijkstra is the closest vertex to S among all the vertices one edge away. That's what I was just talking about. So you've got a contradiction that there can be a path of the idea that there could be a path that's shorter to S than the one that was picked by Dijkstra. So that's the proof. I think what's most important here is you understand why you can't have negative edges. Because if you had negative edge weights on some of the edges, then that last part where you break the proposed sort of path into pieces, a piece of that could actually be negative, and that would give you a shorter path. So it's essential to the proof, and you know that Dijkstra really only works when you know that all the edge weights are non-negative. So again, this slide just reinforces that Dijkstra doesn't work for graphs with negative weights. It works both for undirected and directed graphs. The efficiency is for a weight matrix and an adjacency matrix implementation of or an array implementation of a priority queue. That's going to be O of V squared. Here, for graphs represented by adjacency list and a min-heap implementation of priority queue, it's going to be cardinality of E times the log of V. Notice that E, the cardinality of E, is of order someplace between the cardinality of V and the cardinality of V squared. So you've got constant terms here that make these things not directly comparable. So in general, for any graph that's not too dense, this is going to be preferable. So finally, don't mix up Dijkstra's algorithm with Prim's algorithm. They're very similar. They only differ in a few lines of code. The key idea is that as you're doing the updating of the distances, Dijkstra's algorithm is looking at distances that go all the way back to the start node. In other words, the path, the distance, the length of the path back to the start node. Whereas Prim is just looking to find the closest vertex to the existing partial minimum spanning tree that you've constructed so far, rather than looking at the length of the path all the way back to the start node.